Okay, let's get started. So I'm going to upload Lab 4 today. Lab 4 is about DSBSC and AM. Okay. So okay, let's briefly review what we covered in the last lecture. So basically, in the last lecture, we finished the last property or last two property of the angle modulation, right? One is whether if a signal is nonlinear signal, then what will happen to the angle modulation, and what will happen to the DSBSC modulation, right? And then we briefly talk about modulation, right? Basically, the idea is from the analysis of the bandwidth of the FM signal, and then we can see if the signal is a narrow band signal, then we can have a very simple modulation approach, right? Okay, so let's take a look at this. For the effect of nonlinearity, so basically, we did analysis. Based on that, I just copied my lecture notes here, so that will be much easier for me. So basically, what we do is that if we have a signal like, if I have a system like this, right? So we have A plus the original signal plus B times the cube of the signal, right? And then after some analysis, there's some trigonometric identity used here, and then we get this kind of formula, right? So basically, from here, it is very clear that this part doesn't matter at all because that is a high frequency component. We just filter that out. And then for this part, so we can see that, so basically remember that, so this is the integral of the message signal for FM, right? So this carries the information. So this phi is not changing at all, right, for this. And the only change here is that we have a constant here, right? But this is the magnitude of the carrier, so it doesn't matter. So it basically means that FM is robust to the nonlinearity of a system, right? So this is just one example. And then we talk about the bandwidth of the FM signal. So basically, in order to see the bandwidth, so basically what we do is that, so we rewrite the modulated signal using the complex exponential, and then take the real part of it to get the modulated FM signal, right? And then we use a Taylor series expansion to write this signal as hat. So basically, this is what we get eventually, right? So after some manipulation, so basically what we got is that, so we have this term and this term. So this term is very similar to the DSBSC, and then some higher order term here, right? So for the higher order term, for example, we have a squared here, right? So basically, if the bandwidth of AT, remember AT is the integral of the message signal. So if the bandwidth of AT is B, then basically the bandwidth of this signal is 2B, right? And so on, right? If it's the cube here is a 3B and so on, right? So basically, in theory, the bandwidth of the FM signal is infinity, right? So that's a downside for the FM modulation, right? And okay, but let's say if the KF multiply A, so or this number that's very small, say it's much smaller than 1, then we're good, right? Because this number will be very small, then we can ignore the higher order term, and roughly speaking, the bandwidth would be 2B again, right? So, and also from here, we can see, okay, if we can ignore all of those terms, basically, we can just keep this term and that term. So this is very similar to a, like AM modulator, right? So that's how we do the modulation, basically. So we call that narrowband FM, right? Because the KF times A is small, right? The band will be like small, right? So if it's a narrowband signal, so this is how we do the modulation. So basically, we need to get A of t, right? So that's the integral of the message signal, and then we multiply by a constant KF. So that's the frequency sensitivity factor. And then we do a DSB-SC modulation here, right? The only difference here that we need to use the sine instead of cosine, right? So we generate the cosine, then we shift it by pi half, and then do the modulator, and eventually we need to add this on top of it, right? So to get the modulated signal, okay? So it's very similar to DSB or AM modulator, right? So the only difference here is that we need a sine here, and then we need the integral here, right? Okay, any questions? Okay, so this is where we're finished last time. So now let's see what we're going to cover today. Today we have two topics. The first is modulation for FM, right? So we're gonna see, okay, if the bandwidth of the signal, if it's not narrow band, it's general wide band, then what we're going to do, right? And then we're going to talk about the demodulation. Okay, so yeah, that's the agenda for today. So weird. Okay, here we consider the general FM signals, or consider that as a wideband signal. Right, basically it means that if a KF times AT, that is not much less than 1, then what we're going to do. Okay, so yeah, let's have some assumption here. So assume that the bandwidth of MT is B, right? So we're going to use that later. And then let's see what we're going to do, okay? So any idea? Right, if the bandwidth is not narrow, then what we're going to do? Right, if I'm asking you to design a system, right? So can you, think about what we have covered to do this, or use some signal processing technique to do this. So in practice, it may be very hard to do that exactly, right? Then we are going to basically approximate it, right? Like narrow band modulation, right? We're not exactly doing what we're supposed to do, right? So we're ignore higher order terms, right, and approximate it, right? So now we cannot do that anymore, right? Because the higher order term do have lots of bigger values, right? We cannot do that, right? Is there some other way to do some approximation in order to do it? Yeah, maybe it's not that easy to think about, right? Let's see whether it makes sense or not, right? So basically what I'm going to do is that I'm going to approximate this signal, right? So this is our signal MT, right? So what I'm going to do is that I'm going to approximate this signal. Let's see whether that makes sense or not, right? Yeah, let's see. So basically what we're going to do is that we're going to sample it. Right, so we're going to sample this. Yeah, we're going to cover the exact meaning of sampling later on when we talk about digital communication. But here, just understand sampling as, okay, we just take a value from here and take a value from here of MT, and then the interval of the sampling is capital T, right? Just let's assume that, right? So basically it means that, from here to here, we're just using a constant, right? From here to here, we're just using a constant. And similarly, yeah, let's use a constant. Oh, no. Yeah, to approximate. Yeah, we are using the green one to approximate the black one, right? We call that as M hat of T. Does that make sense? Sort of? Okay, so this is basically what we're going to do, right? So basically, now I'll give you how we're gonna pick this T here. Okay, so basically, given the bandwidth of the MT is B, right? So the T is going to be 1 over 2B. Okay. By the way, who knows how do we get this? So anybody see this kind of thing before? Like the sampling rate? What is that? Nyquist rate, exactly, yeah. So we're going to do that later. So yeah, just see whether you know that or not. But we assume that is given, right? So basically it means that if we sample a signal with a rate that double the bandwidth, then we're good. We can recover the signal exactly, right? But it has nothing to do with what we're doing now. So basically, let's assume that, right? So this is sampling rate, right? T is equal to 1 over 2b. Okay, so basically, yeah, let's write it down carefully on what do we mean by this, right? So basically, it means that, so let's assume here that is, let's say here's tk, right? So basically, we assume that when t equals to tk plus t, oh no, tk to tk plus t, right? So when tk is this range, so basically we assume m hat t equals to, yeah, now we're assuming to the left value, right? So basically here it means that mt equals to mtk, okay, for this entire range, right? Basically, it means exactly like we'll take a flat value here. That make sense? Right? Okay, so yeah, if that is the case, so now let's see what our modulated signal look like, right? Remember our, let me write here. So this is our, I use hat here because now we're using m hat, right? So this is our modulated signal. So that equals to cosine omega ct plus, so before, remember before what we should have this one, right? So this is a frequency, okay? But because now we're doing this approximation, so basically we don't have that exactly. What we have is mk, tk here. Can you see that? The t sub k, okay? But for this value, it's not equal to t sub k all the time, right? What it does is that only in this range or this range, it equals to m of tk, right? So basically, we need to multiply this square function here, right? So we multiply this kind of rectangle wave, which is t over capital T, right? Does that make sense? Right. So basically, we just need to take this, take this value out. Right. That's basically the trick that we do. Questions? Right? So if you write it down, you can plot it, then you're going to get this approximation. Okay? For each this value, then we're going to take the entire thing to approximate the original thing. Right? If you think if tk, if capital T is small, then the approximation would be very accurate. If T is very large, then this approximation will not be very accurate. Right? But the bottom line is that the T has to be this value. Does that make sense? Yeah, this is the only trick that we're doing here. Okay. And then we just do this modulation, and then that's it. Yeah, does that make sense? Any questions? Good? Yeah, just ask if you're not clear. So this is basically the modulation. And okay, so because now we're kind of using another signal to replace our original signal, right? So we're going to see how it looks like in the frequency domain. Right? So that still be good, right? What would be the bandwidth of the signal, right? Because in general, right, if it's here, even here is not T, here tk, here is T, then we can see the bandwidth is kind of infinity, right? But now let's see, so what if we replace this by tk and we add a rectangle function here, and then what would be the bandwidth look like, right? That's our goal, and whether that is meaningful or not, okay? Okay, so basically, yeah, let's do it. So basically, what we do is that we're going to compute the Fourier transform of this, right? Because normally in the time domain, it's very difficult to see the useful property. We use the Fourier transform, okay? So how do we do this? Okay, so basically now we can see we have two terms here, right? So I have a cosine term, so that's a carrier, and then we have a rectangle function, okay? So basically what we do is in the time domain, it is multiplication. So in the frequency domain, that will be a what? Convolution, right? And the frequency here is very easy, right? So it's just cosine, just summation of two delta, right? So the trick part is that what's the Fourier transform of that? Anybody remember it? So we did that so many times, right? Still don't remember it? It's just standard form, right? T over capital T. But you do remember it's a sink, right? right? You just don't remember the, the coefficient, right? So yeah, it's not that hard to remember actually. So we put a t here. I think here is pi ft. So if I remember correctly, yeah. Okay, and because we're gonna write everything in omega, so that's basically equals to what? Equals to omega t divided by 2, right? Because we need to put a 2 here, then we divide by 2, right? So that's what the signal looks like. And given this, we can write the Fourier transform of our S hat, right? Then, oh man, the Fourier transform of our hat is, we just use this convolute the 2 delta function here, right? So basically what we got is that this equals to half of capital T sinc omega plus this frequency, right? Omega c plus kfmt kt divided by 2. Yeah, let's remove this. Yeah, remember, so we have a Wt over 2, right? Yeah, so basically I'm gonna, just to keep consistent with my notes, right? So we know t equals to 1 over 2b, right? So I have t on the top, then we put a 2b on the downstairs, right? So basically we have a 4b here. Okay, and then we need to add another term, t sine, not sine, sinc. W minus omega c minus kf mtk divided by 4b, right? So this would be the Fourier transform of it. Okay? So it's kind of simple, right? So now let's take a look at what it looks like. Let's sketch it. So basically, yeah, for a fixed k, it will look like this. So we have a sinc signal here, and we have sinc signal here. Okay, and the frequency component here is that here is a minus omega c minus kf mtk, yeah, and here is omega c plus kf mtk, right? Those are the 2 frequency components, right? So those are for this signal exactly, right? How about for a different k? Right? If k changed, right? This is for just if for 1 tk, right? If k changed, right? Then what should I have? So we should have very similar pair, but in different location, right? For example, for different k, so we may have. So we may have, we can have something here, right? And so we may have if the value of m is bigger, then we can have something here as well, right? So let's draw. Yeah, it's not symmetric, but it should be symmetric. So basically, yeah, we're gonna have lots of this kind of thing, right? For different k, because for different k, so we're gonna have different value of mtk, right? Mtk determine where the shift is. That makes sense? Okay. So now let's denote. So basically now we're going to want to figure out the bandwidth of the signal, right? Remember, so it's a sinc signal, right? So basically the value of here, not the value, the width of here is just nothing but 1 over capital T, right? Or right here, 1 over capital T. Okay, so now let's figure out the total width of it, right? So let's denote MP as the maximum value of MT, right? So that's the highest, kind of the highest frequency shift, right? Doesn't mean where the signal will end, right? But this is the highest frequency shift, right? Because from here we can see, so this is the frequency shift, right? Compared to omega c, right? The maximum value of this guy would be the highest frequency shift, right? So basically, yeah, let's see, this is our MP, or omega c plus MP. And I see here is our minus omega c minus MP, right? So that will be our K. You have a KF, have a KF here, right? That's the highest frequency shift, right? So now let's see. So given this, right? So there will be nothing, beyond this point, okay? And given this, what do you think it will be good to define the bandwidth of the signal, right? Because signal will continue forever. It's a sinc function, right? Sinc will continue forever, right? But what are the meaningful bandwidths that we're going to define, given this, right? Because this is the highest frequency shift already, right? There will be nothing of sinc beyond this point, right? So where do you think we should consider the signal ends? Right? Should we consider signal ends here? No, right? We'll have like half of this, right? How about here? Does that make sense? Sort of, right? So I think this is a meaningful point, right? So basically, we consider signal ends here, okay? Omega c plus k f mp, right? So basically, it means this. So basically, we have a signal with a frequency omega c plus k mp, right? So that's basically what? The highest frequency shift, right? But the lowest frequency shift is what? Another one, right? So basically, it could be, yeah, maybe let me use this. So the lowest frequency shift is around here, right? So that is what? Omega c minus kf mp, right? There will be nothing after this point while keeping it positive, right? Because that would be the last one, right? Because this is maximum magnitude of MT, right? That makes sense, right? So let's say, yeah, here, let's say here 0, then those are the negative frequency component, and those are the high frequency, the positive frequency component, right? So in this case, so basically this will be counted as the bandwidth, right? Or, not or, so we're gonna compute that, but basically this, so that will be counted as the entire bandwidth, right? So given this, so now we can see the value between the difference between this and that would be 2 kf mp, right? Okay, and then we need to add this part and this part, right? So remember, so the length of that is this guy, right? 1 over t, right? We just need to add 2 times 1 over t, and that is a good estimate for our bandwidth. That makes sense? Yeah, we need to be very careful here. Okay, so yeah, if that makes sense, let's reorganize it a little bit to have a better look at this. So basically, the bandwidth equals to 2 times kf mp plus 2 over t, right? So let's remember 1 over t equals to 2b. Right? We have t equal to 1 over 2b. Yes?
Wouldn't it be plus 1 over t since it's on the side of the parentheses?
What? Oh, yeah. Wait, yeah. Here should be 1, right? Very good. Is that a question? Yeah, great. Yeah, this is 1. So yeah, remember this is this equals to 2b. So basically, this guy equals to 2b, right? And then we have 2 times kf mp plus 2b. Okay, so that's the total bandwidth of the modulated signal. That makes sense? Okay, so if that makes sense to you, then we can take a look at this, right? So basically, let's remember. So for the DSBSC, right, the bandwidth of the modulated signal is simply 2b, right? But for this one, so I have 2b here, and then multiply 2, it's 4b, and then we have to add this part for the total bandwidth, right? Normally, it's a huge number. Okay, and that is the estimation of our bandwidth, right? So in general, this is very conservative. Okay, so this is too conservative. Or too pessimistic, right? So basically, yeah, if we, this normally give you a huge number, but in reality, we can consider signal bandwidth much more than that, right? Basically means that we can ignore more part of it, right? Because, yeah, the magnitude of this guy may not be equal, right? So, okay, so given that, so let's introduce some other concept to indicate the maximum frequency shift, right? So we give a definition here. So that is called peak frequency deviation. Okay, so basically the peak frequency deviation, so we denote that as a delta F, okay? So this delta F is the maximum frequency of the sinusoid. In phase or frequency modulation. Okay, so basically, so what do we mean by this? So basically, in this case, it basically, let me see. So it means this term, right? Or this term. So basically, the delta F is defined by, let's see, the maximum frequency of the sinusoid modulation in phase or frequency modulation, right? So in general, it's defined as this. So basically, if we denote the maximum value of m as max and the minimum value of m as min, so basically it means that it's m max minus m min divided by 2, and then we take we multiply kf, right? So in this case, it'll be, yeah, if it's metric, so basically, so that will be our good estimate of delta F, okay? And given this definition, so therefore, we can write this as 2 times delta F times 2b, okay? Yeah, we need to be careful here, right? So this delta F called peak frequency deviation. So it doesn't mean the maximum frequency of the modulated signal. Does that make sense? So it's the deviation that is showing here in the frequency, the maximum frequency deviation. So it's not the maximum frequency of the entire signal. Does that make sense? Right, because it's complicated, right? To see the maximum frequency of the entire signal, we need to do what we did in the last lecture. We need to compute the Fourier transform of it, and then analyze the frequency domain signal, right? Because we have something like here, which is function of t, that's very complicated, right? Kind of confusing here, but we need to distinguish between these two, right? Delta F is the maximum frequency deviation in terms of the frequency here, only here, okay? Yeah, just need to be clear on that. And then let's see. Okay, yeah, I think we're almost done. So basically, yeah, as we said, so this bandwidth is very conservative. Right, the reason here is that we have 2b here, right? And then, so if it's 2b multiplied 2, I have 4b here, right? So like 4 times of the original bandwidth of the message signal, right? So basically, in order to have a better or more efficient estimate, we have a rule called Carson's rule. So basically, Carson's rule said the bandwidth of FM, we denote that as BFM. So that can be estimated as the following: delta F plus B. Right, so basically we ignore this 2 here. We just write a single B here. Turns out that this is a good estimate of the bandwidth of the FM signal. Okay, yeah, I think that is an empirical estimation. So normally when we design a signal, we can pretty safely to assume this would be our bandwidth of the modulated signal. Okay, yeah, does that make sense? Okay, and given this, yeah, let's introduce one more concept here. So basically, we have a definition. So this is sort of like the modulation index in the DSB-SC. So who still remember that? So what is modulation index?
Like how close the minimum of the message signal is to 0, or like when we were measuring like the envelope of it.
Exactly, very good, right? But here we have something very similar. So we have frequency modulation index. Right, so basically for this frequency modulation index, so that is measured between delta F and the bandwidth of the signal, right? So before it's the deviation between the deviation and the bandwidth of signal, right? Before for the amplitude modulation, so that's the deviation in the magnitude and compared to the absolute value of the maximum amplitude of the signal, right? So kind of very similar. But here it's in the frequency. Let me write it down. So the frequency modulation index, we denote it by beta. And so basically, this beta is the frequency deviation as proportion of message bandwidth. Okay. So basically, in other words, so beta equals to delta F divided by capital B, right? So it has the same essence as the modulation index for the amplitude modulation. Okay. And given this concept, so basically we can write the bandwidth of FM signal as the following, right? So basically there we have 2 times delta F times B, right? So here we can take the B out, right? We have 2B times delta F over B plus 1, right? So that is 2B beta plus 1, right? So this is basically the bandwidth. And we can see that clearly here, this 2B is the DSB SC or AM, the bandwidth of DSB SC and AM signal, right? So here, if we use frequency modulation, so this is how much more we need to give it, okay? And clearly here, let's see 2 cases. So if for narrow band FM, so NB means narrow band FM, right? There basically means that the deviation here is very small, right? So basically it means that beta is very close to 0, right? Then the bandwidth of the narrow band FM, so that is very close to 2B, right? Which makes sense, right? Because we use the DSB-SC modulator or AM modulator for this guy, right? It has a similar bandwidth. But for the general, for the general, then we just we need to pay the value of beta here, right? We need to spend more bandwidth on this. Okay, that makes sense. Okay, yeah, that's the modulation part I want to talk about. Okay, next let's take a look at the demodulation. Yeah, for the demodulation, so we're going to talk about two approaches. Okay, so the first approach is like a straightforward approach. And the second approach is PLL, the phase locked loop. Okay, so for the demodulation, can you think of an easy way to demodulate this signal? Maybe let me write it here to make sure you remember it. Yeah, for simplicity, let's assume that the modulated signal is like this, right? So A cosine omega c plus t plus kf, right? For simplicity, let's assume this is our modulated signal, and I want to recover this m, right? How could we do it? Right? What kind of operator that can take this out from it? Right, it's an integral, right? Right. So normally, how can we get this from an integral of it? Yeah. Can I do that? Yeah. How about we take a derivative of the whole thing? So can we get something like that in front? Yes, right. So basically, that's the idea. So it's not very hard. So basically, yeah, think about that, right? So basically, given that it's a modulated signal, and then we do a derivative of st with respect to t, and then basically what we're going to get is a. So remember, so the derivative is with respect to t, right? So when you do a derivative of this, get a sign, and then do a derivative of the whole thing. That's a chain rule of derivative. So basically, what inside is omega c plus, so for the second term, we just get mt, right? And we have constant kf in front, and then we have a sign. Yeah, the derivative of cosine is just a sign, right? So yeah, this is what we got. Okay, so are we happy now? So for this term, can we do a demodulation? Did we see this kind of thing before? Right, let's see, we don't have it. Well, we don't have this. Is that familiar? Yeah.
We could do the same demodulation we did for amplitude modulation.
Exactly. Yeah, that's exactly what we're going to do here, right? So this kind of thing doesn't matter at all, right? So basically, we just do an amplitude demodulate, amplitude or envelope detector to get this part out, right? Because this is just a sign, and then we just need to get the envelope out, right? So this changing doesn't matter, right? This is just a little bit change in the frequency. If we do the envelope detection, so this will not matter at all. So therefore, so the name of it is called differentiator and envelope detector. Okay, and let's make it more explicit. We can see that. So this is just a constant, right? Like the constant of the carrier in our AM signal, right? And this is our message, right? So this whole thing is like the AM modulated signal, right? We just use the envelope detector to decode it. And so after the envelope detector, so basically we got the envelope detector gives the following, right? Just the magnitude, which is A times omega C plus KF MT. Okay, and that's basically what it is, right? But in practice, this A may have some problems. So normally this A is a function of T. Okay, there's some changes, in this A. So in order to make it as a constant, we're just using a limiter to get rid of the changing in A, right? So basically, a limiter is that if the signal passes through a value, then we're gonna cut it. Okay, something like this, like a U function. If it's bigger than this guy, the value here, then it'll cut it, in flat. So we're gonna use it a lot, for the FM demodulator. Okay, so now let's write the diagram of it. So basically what we do is that we have an input signal, which is our modulated signal, right? And then we're passing that through a limiter first. Okay, so this is just a sine function in this case, right? So we have something in the middle. Okay, to limit the value of A, and then we pass that through a bandpass filter to get the whole thing out, right? Because the bandwidth of it, we have a, the bandwidth of it, not bandwidth, it means the equivalent bandwidth is like this, right? So we need to pass it through a bandpass filter to get the signal out, okay? So we pass through that with a bandpass filter, okay, and the center at omega C, right? And then after that we have our signal, right? And then we're passing that through a derivative operation, and then do an envelope detector. So then we can have our empty out, right? So that's basically what we do here. Okay, great. Any questions? Yeah, this is kind of an easy way to do demodulator. Okay, and we can see here. So basically, so this is using a AM demodulator, right? So usually so it has all the drawbacks of the AM demodulator, right? So a better one would be a coherent demodulator, okay? So this comes to the concept of, yeah, we're out of time, so I just maybe tells you a little bit motivation of it. So a better and coherent demodulator is called phase-locked loop, PLL. Right, so normally, so this phase-locked loop is to get the phase of the cosine signal. Okay, as we said before, right? So a big problem for the coherent detection of the AM or amplitude modulation is that we cannot get the exact phase, right, of the transmitted signal. Okay, so the phase-locked loop can help you to get it. So basically, you can use that to help you to decode the DSB SC signal, okay, for the coherent detection. But here, we use this, so it's a kind of an extremely smart design that we can use that as a demodulator for the FM signal, okay? So yeah, it's a very smart design. So we're gonna look this in very detail in the next lecture. Yeah, it's a very complicated structure, but it can track the phase. Okay, great. Thank you.